Hello everybody. In this video, we will do some exercise on the Laplace transformations. This is the second on the series. The first one was a little summary of Laplace about the Laplace transformation. So this is the second one. We are going to solve Laplace transform on very simple examples, basically to understand how we are using Laplace transform to define on certain functions. Let's start with the simple one, very simple. This is a polynomial. All we need to do is really practice is this part of the table. So Laplace transform of t to the m is a natural number, m is a here 0, 1, and so on. Then the Laplace transform of t to the m is m factorial over s m plus 1. If we think that m is equal to 0, then we will have t to the 0 is just 1. So Laplace transform of 1 is 1 over s, because 0 factorial is 1, m is equal to 0, that will give you s. This is the polynomial, and we apply the Laplace transform to the polynomial. By linearity, linearity means taking the constant terms out of the function in front of the function. And if we have a summations of the functions, we can split. Then this can be written as Laplace transform of t squared plus 2 times 2 is a constant, goes the front and goes out in another way of saying it. Then the Laplace transform of t plus 3 times Laplace transform of 1. So the t square, Laplace transform of t square, that is the case when m is equal to 2, that is 2 factorial over s3, which is that guy. That is 2 times Laplace transform of t, that will be m is equal to 1. 1 factorial is 1, right? 1 factorial divided by s squared. That is 3, as I explained at L or 1, it will be 1 over s. As 0 factorial over s, that is just 1 over s. So 2 factorial is 2, 1 factorial is 1, so we have 2 over s cubed plus 2 over s squared plus 3 over s. It's very clear, I suppose. It is again direct calculation from the table of the sine function of wt. W is a constant here, is given by W divided by S squared plus W squared. And we want to calculate the Laplace transform of sine 5t, and say W is 5 in this case, so the transformation gives us the 5 divided by S squared plus 5 squared, which is 25. Okay, if we want to calculate the transformation, Laplace transformations of the function exponential 3t minus 4. We were going to use the table, and the tables tell us that the Laplace transform e to the something alpha times t is 1 over s plus alpha. So if this is my, for the here, alpha is a positive number, any positive number. Maybe I should emphasize it there, so without having an ambiguity. So Laplace transform of this function, exponential 3t minus 4. I'm splitting this up, exponential minus 4 times an exponential 3t. This is a constant. This is not a function because it does not have a t in it, right? So I can take this constant out because I know that the Laplace transform is linear. So taking out, I have the function exponential 3t, and I know the Laplace transform of this, which is 1 over s minus 3, alpha is equal to 3 case. Alpha is equal to minus 3 case, sorry. Okay, another one is t times e to the exponential t. So this one is given in the table as Laplace transform of t gt is minus the Laplace transform of gt and the derivative of it. This is given by in the table. We are going to use this fact. So we have t, right? That's t. So gt for us, exponential 2t. So Laplace transformation exponential 2t, we will calculate that. We will take the derivative, and that's a negative. Negative stays there. E to the Laplace transform of exponential 2t will be 1 over s minus 2. Now we are going to take the derivation. For the derivation, we apply the quotient rule, which says that u over v, u prime v minus v prime u divided by v squared. So the derivative of u here will be 0, so I don't need to write it. Derivative of this is just 1, so that's minus 1 times 1, which is just minus 1, divided by v squared is minus 2 squared. So minus minus will be plus, that will be 1 over s2 squared. Okay. Now, next question. This is a bit more complicated than what we've done before. So the function is given here, gt, is 2t minus 2 t ut minus 1. Ut minus 1 here, as you've done in the lectures, is a Heaviside function. It's ut minus a. When t is smaller than a, that's 0. When t is equal to a, it is 1 over 2. It's just 1 point. When t is bigger than a, you have 1, which is a line segment. And Heaviside of this function has the graph in that kind. Up to a is a graph, and then in the a, I have only 1 point, 1 over 2. And then the for the t is bigger than a is just 1. That's the 1. So that line segment. If you take the negative of this function, then you will have a 0 minus 1 over 2 minus 1. That will just flips in that fashion. So up to a is 0, except a. In the point a, I have minus 1 over 2. And for the t is bigger than a, we have minus 1. So that negative size will be like this. Now, let's have a look. So this is a side note here. This thing here is a side note. This is just an introduction. This is to help us to understand. Actually, solution starts from here. And gt is given by this formula. I can rewrite gt by plugging in the information that I know about the u. If t is a here is 1. If t is smaller than 1, that is 0. So it's just 2t. When t is equal to 1, this is 1 over 2, but you multiply by 2, that will be 1. So that's 2t minus 1, right? When t is bigger than 1 is 1, we multiply by 2, minus 2. That's minus 2, 2t minus 2. So this function can be written in this fashion. Let's have a look at the graph, how the graph looks like. So up to when t is smaller than 1, this is 1 here, when ct is smaller than 1, 2t is a line, right? We know that because this is an x line. We think about x and y, then it will give you a line equation with the slope too. It's the same idea. This is t, this is gt. So gt is equal to 2t is a line with the slope is 2. If you have 2t minus 1, that is the line with the same slope, 2 slope with the slope of t, which means the parallel of this line, right? This is y is equal to 2x line, this line here. And if we shift it to minus 1, it means that we are thinking about the parallel line, which passes through minus 1, which is this point that passes through minus 1. And 2t minus 2 is the line. This line here passes through minus 2. Well, my drawing is not perfect, but these 3 lines are parallel. This one passes through the 0. This one passes through minus 1. This one passes through minus 2. That corresponds to 2t minus 1, 2t minus 2. And up to 1, t is equal to 1, we have this part. When t is equal to 1, we have a point on this line. And when t is bigger than 1, we have a line segment, except this point towards this. So this will be the graph of this function, which we draw as we required. Now, let's calculate the Laplace transform of it. And gt, so we have the addition of two functions. We can split it up by the linearity of the linear transformation. So Laplace transform is linear, so we have the constant times LT, Laplace transform of t, minus 2 times Laplace transform of ut minus 1. Now from the table, Laplace transform of ut minus a is given by e to the minus a over s. So in this case, we will have if a is equal to 1, we will have e to the minus s over s, right? When Laplace transform of t will be just m is equal to 1 case, 1 factorial over s, 1 plus 1, which is 2s squared. So Laplace transform of t will be 1 over s squared. So by using this knowledge, substituting in, we will have 1 over s squared minus 2 times that, which is e to the minus s over s. Tidying up a little bit, so we have 2 to the s squared minus 2 to the e to the s over s. Okay, that's all. It's just a substitution from the table knowledge. Now let's have a look at this one. So as we know, we can use the table as like a Laplace transform or an inverse Laplace transform. So this function is in terms of given by in terms of s. Then we can apply to the inverse Laplace transform. We will obtain a function in terms of t. Okay, then Laplace transform of t to the m is given by m factorial over sm plus 1. So the inverse of this will be t to the m. Yeah? This is vice versa. And the Laplace transform of I need to have an inverse here. If you have s inside, that means that you have an inverse. If you have a t inside, it means that you have an L. Right? Because you're thinking about the function space with the ft here, and then you're applying L, and then you find fs. And if you apply the fs, going back to ft, that will be L inverse. But you can use the table on both ways. Okay. So we would like to calculate the inverse Laplace transform of this. So we have s squared here. So 1 over, again, inverse Laplace transform is linear. So the constant terms can go out. We have a constant term here. We can take it out. And inverse 1 over s squared. So it looks like this. It means 1 over s squared. So m is equal to, m plus 1 is equal to 2. In that case, m is equal to 1. So it will be just t, right? L of t is 1 over s squared. L inverse 1 over s squared is t. So I have only t for that. And for this section, we look at as s over s squared over 5 squared, which looks like this in the table. That is the cosine 5t. That's all we need to do. So inverse Laplace function of this is just 1 over 25t plus cos 5t. It's just a substitution. It's just to use the table, just a substitution. It's very straightforward calculation. Okay, let's have a look at this question now. We have a rational function is given here. S minus 2 divided by s squared minus 4s plus 5. So we have two options to do that. We need to think either a partial fractions. It may be in that way, to be solvable. Or if not, we are going to think about cosine, sine, or sine hyperbolic and cosine hyperbolic, right? The Laplace transform of cosine is s over s squared over w squared. So either cosine, sine type of questions, or maybe it is factorized, and now we need to think about the partial fractions. In this case, s squared minus 4s plus 5 cannot be factorized. So we don't think about the partial fractions. How we write s squared minus 4s plus 5? We want to write this in terms of s minus 2. So that will be similar case like this. Well, it is a shift, right? Because s, instead of s, we have s minus 2. We have s minus 2 on the top. And now this is s squared minus 2 squared plus 1. Let's first make sure that this is the right one, right? We have s squared minus 4fs. And then we have 4, 2 squared is 4. But we have 1 here, that will be 5. So this is equal to this. First, just trust that one. Now substitute in. Now we have s minus 2 squared plus 1. It looks like except it looks like a cosine, right? Laplace transform of cosine looks like that, except that instead of s, we have s minus 2. It means we have a shift, right? Then we need to use a shifting theorem. The shifting theorem says that if we have a function fs minus a, then we need to shift our function with the exponential function a to the at. This is a shifting theorem that we've seen. Okay, that means that fs minus 2, right? This is what it is. S minus 2, s minus 2, s minus 2 squared plus 1. I shouldn't say that, right? So f minus 2, I'm applying the Laplace transform and writing down that. Sorry. This means so the Laplace transform of inverse of s minus 2 will be e to the at, which is a is equal to 2, exponential 2. And this one is a cosine function when w is equal to 1. This is 1 square 1. So that's cosine t. Maybe I will explain a little bit more. So we want a inverse Laplace transform of this one. So we know that inverse Laplace transform s over s squared plus w squared is cosine wt. Since we have 1 here, we also know that s over s squared plus 1 is cosine t. But in our case, instead of s, we have s minus 2. That means it is a shift. Right? If you're replacing some s with the s plus a or s minus a, it means you have a shift. You need to use the shifting theorem in that case. So we have s minus 2 instead of s. That helps say to us that we need to use shifting theorem. And the shifting theorem says that if we have the shift fs minus a, then e to the at ft will be the way that it goes, right? So the shifting factor here is exponential a to the t. So ft here is the inverse Laplace transform of f. What is f for us? Fs maybe that was missing here. Fs here is s squared over s squared plus 1. This is our Fs. If you put Fs minus 2, then we will s minus 2 divided by s minus 2 squared plus 1. Fs, the inverse Laplace transform Ft. So that is cos t, right? The inverse of this is cos t, and the shifting factor is exponential. What is the shifting factor for us is 2. So this is 2t. I hope it is clear now. Okay, next example about the partial fractions. So we have linear factors here. So we need to think about the partial fractions. It means why? Why? Because an inverse is a linear function. We cannot think of the, we cannot split the functions in multiplicative form, but we can split the functions under the L or L inverse transform if they are in a addition form. We cannot split. We cannot think about the L of this is L of this part times this part. It is impossible. It is not correct. But we can think of the linear inverse Laplace transform of this plus inverse Laplace transform of this. Okay, we can split that. We can split like this. Instead of Laplace transform of all of this is that. That makes, okay, can we calculate the first quick way of the partial fractions for s plus 3, s plus 2. So the root of this, s plus 3, is 3 minus 3. So remove this part and substitute minus 3. So we substitute minus 3. Minus 3 plus 2 will be minus 1. It's 1 over minus 1. Plus s plus 2, the root is minus 2. Remove that one from your eyes. Substitute minus 2. So this is minus 2 plus 3. That will be 1. So this is 1 over 1. That's 1 over 1 on the denominator. That's a quick way of calculating the splitting partial fractions. So this can be written in this form. By using the linearity, we can split. Then we can calculate this bit and this bit. By using the table, the table says that 1 over s minus a is the exponential minus at. So a here will be 2, so e to the minus 2t, and minus is this minus, 1 over s plus 3 will be a is equal to 3k's, exponential minus 3t, which is that guy. Yeah, clear? Okay, let's have a look the other one. Again, we need to use the shifting theorem. Now, we would like to calculate the inverse function of exponential minus 3s over s squared. From the table, we know that the Laplace transform of the Laplace inverse transform ut minus a is e to the e minus as over s. And almost there, right? That's that. Now, okay. How we can think of exponential 3s over s squared as in terms of the shifting theorem, right? It looks like this, right? So we would like to think that this is e to the minus 3s is different. Then we have fs. Fs is 1 over s squared. Fs is 1 over s squared. And ft is the inverse function of 1 over s squared, which is just t. That is the case t to the m is equal to 1 case. We know that Lt is 1 over s squared. So L inverse 1 over s squared is t, right? And L inverse exponential minus 3 times fs, which is this function, is equal to, this is, I'm going to use the shifting theorem too. The shifting theorem 2 says that this is an inverse Laplace transform. E to the minus as fs is equal to ft minus a ut minus a. So this is the theorem that is saying I'm using this line into here. That's all I am doing, right? ft minus 3, ut minus 3. But ft minus 3 is basically, what is ft here? Is is just t. So ft minus 3 is just t minus 3. I'm just substituting this knowledge into here. That's all I'm doing. Is that clear? It is basically the substitution right ones in a right way. That's all. I hope it is clear. And try to do it by yourself. But think of this as an e to the minus s to the fs. Fs is 1 over s squared, and 1 over the ft is the Laplace inverse Laplace transform of 1 over s squared, which is just t. And the shifting theorem gives you this equation, and ft is t, so ft minus 3 is t minus 3. So maybe if I write that, that will be 3. So ft is equal to t, and ft minus 3 will be just t minus 3. Okay, that's all. That's all for this video. In the next one, I will look at the applications of the Laplace transform into ODEs, how we solve ordinary differential equations. Thank you very much.